we go. Welcome to section 1.1 and calculus 1, week 1 of a new semester. So we are going to kind of start off in chapter 1 dealing with some review stuff, and I'll tell you that it's really compact with a lot of information. So I'm really hoping that you're coming to me with a good foundation in functions, in Algebra 2 material, college algebra material, and so that you could be successful in calculus as well. If at any time that you're feeling stressed about review, please let me know and we can get you kind of caught up to speed. So, in order to be successful in calculus, one must have a strong foundation in the elements of mathematics, algebraic skills, notation and terminology for various sets of real numbers, and the descriptions of lines, circles, and other basic sets in our coordinate plane. In this chapter, we will be reviewing some functions which are crucial in calculus, like polynomials, rational functions, algebraic functions, and trigonometric functions. So polynomials are y equals x cubed minus 3x squared plus 2. Rational functions are those that are fractions. Algebraic functions could be things like a square root function, a cube root function, anything like that, exponential function, such. And then our trigonometric functions obviously will include some trig functions, sine, cosine, cotangent, etc. Everywhere around us we see relationships among quantities, or what we refer to as variables. For example, the consumer price index changes in time and the temperature of the ocean varies with latitude. So these relationships can often be expressed by mathematical objects that we call functions. Okay, so let's get into a definition of function. And we're going to kind of just review this again, so it should be pretty quick if it is a review for you. So a function, normally we refer to them as f, is a rule that assigns to each value x in the set of D a unique value denoted as f of x, or I want you to think of that also as a y value. And we can refer to the set D as the domain of the function, which is the set of all x's. Okay, so what are all the inputs that I have within my rule? And then what we refer to as the range of our set is the set of all values of f of x, or don't forget that's the same as y, produced as x varies over the entire domain. So our domain we can think of as the input. Our range is then the output of our function or our rule. And we can also go as far as to talk about the independent variable as our input. And once we put that in, then the f of x or the y is then the dependent variable depending upon the rule that I have there. So after we have a rule or a function, the graph of that function is very important, and we're going to see that kind of in our next section, a big review over the different types of graphs that you should be coming to me with. But the graph of f is the set of all points, and we can refer to them as an xy pair in the xy plane, or what we call the coordinate plane, that satisfies the equation y equals f of x. And don't forget, f of x is our function, okay? That's our rule. It could be 2x plus 1. It could be x squared minus 3x plus 2. It could be that I have e to the x. We'll talk about the natural exponential as well. So here's kind of just some graphics for you to see. That's like kind of pulled out of the book. If you're looking through your book on My Lab Math, or if you went ahead and bought the tangible book, you should see some of these things. So again, if I input, here's my rule that I have, and then I'm going to kick out some values. There could be different values here within our domain. Here are the y values that are kicked out within my range, and that f then just maps those to different pieces, okay? I could also write it in terms of x as a rule. And I could also do a second function. Normally we refer to use f and g as a common variables that we have for functions. You can use anything. You could use any letter that you want. You can use Greek letters, anything like that out front. It is just a name. All right. So as a review here, evaluating functions would be something that looks like this, where I'm looking for what is f of 2. And that means that wherever I see an x in the f function, then I'm going to replace that with 2. So f of 2, we would take the x out, replace it with a 2, and then add 2. By order of operations, we're going to multiply first and then add. So f of 2 is equal to 8. We could also ask for what is g of negative 3. G of negative 3 means that I'm going to take negative 3 and plug that into the g function and figure out what that is. So that tells me to take my number and square it, then add twice of that number. And again, by order of operations, we're going to simplify this. So we're going to be able to make this a 9, and then 2 times the negative 3 is a minus 6. Therefore, 9 minus 6 gives me a 3. But there are some cases in which there is not a number. We're just looking at expressions within that, and this is going to be crucial when we start talking about derivatives and kind of the definition of that, to be able to evaluate a function at an expression. So I'm going to go to the f function, and I'm going to place in x squared wherever I see an x. So that means I'm going to replace that right there, and that means that I have 3, take out the x, input an x squared, and then add 2. So this, I can't combine the 3x squared and 2, is the best that I can write that expression. Likewise with the g, here I have, I'm going to put a plus 2 in there and a plus 2 in there. So this one's going to be a little bit longer because I have a quantity squared here. Plus 2 times a plus 2. Okay, so I'm hoping through some of your previous instruction in mathematics that you please do not make the mistake of saying this is a squared plus 4. If you just square the a and square the 2, that would be incorrect completely. This is a binomial that, if you recall, a plus 2 squared. Let me change my thickness here. Okay, this is equal to a plus 2 times an a plus 2. And so when I have to multiply two binomials, if you recall, that is a foiling situation in which I have to do my first outer inner last. So this would be a times a is a squared. Outside gives me a, 2a. Inside gives me a plus 2a as well. And then the last term here, 2 times 2 gives me a 4. So then I can combine like terms with these middle two and get a 4a. So this actually becomes a squared plus 4a plus 4. Okay, so if you just say a squared plus 4, you're missing that complete middle term. That is very, very crucial in that case. Now, when I was teaching high school and I did this with my Algebra 2 students, I forced them to know the pattern of that. In mathematics, it's so important to know some of the patterns, and it also makes it a lot quicker if you do know those patterns. So if I have a quantity squared, okay, and the pattern of that, let me do that up over here if you want to write this. If I go a plus b quantity squared, if you were to do that, take out the 2 and put in a b, then here is the pattern of that. You're going to square the first to get an a squared. Then you're going to multiply these two guys here and double it. Now, this a times a positive b is a positive ab. If I double, that gives me a 2ab. And then I'm going to square the last, which gives me a b squared. So you can use those variables there to get that pattern, but if you know the pattern, square the first, multiply the 2 and double, and square the last, you should be successful. Now, the only difference is if I end up having a minus here, okay, there's only one small difference, and that is that this first sign would end up being a minus as well. So those signs match, but the pattern doesn't change. It's still square the first, multiply the 2 and double, and square the last. Now I'm going to go ahead and distribute here so we can finish off our g of a plus 2. So So I'm going to do plus 2a and plus 4. And so this ends up getting me a squared. Combine these two a's would be a 6a. And combining those two 4's that I have there as my constants gives me a plus 8 at the end. So a squared plus 6a plus 8 is going to be my final answer. Little delay there. Sorry about that. Okay, so that is evaluating functions. Function is just a rule. We will work with them all of the time. If we want to think about a function, what makes up a function, that is that only one x value or one x value will go to a unique y value. So an x value can't have two different y values. That would not be a function. But we can have two different x values going to the same y value, and that's okay. Now, how can we graphically determine if we have a statement that is a function? Hopefully you can recall something called the vertical line test, and that is, by definition, that a graph represents a function if and only if it passes the vertical line test. And what that means is that every vertical line intersects the graph at most once. It cannot intersect it twice with any vertical line. If it does, then it fails to be a function. So let's move on to our second page. Given 4 graphs here, state whether each graph represents a function. So by the vertical line test, if I have a graph, I can go through here and just start drawing a bunch of vertical lines, and if I only intersect that function one place, then yes, this is going to be a function. If I look at this guy right here, somewhat looks like a $sign now, and I have those 3 places that that one vertical line intersects, this is not a function. Functions are important in calculus, so it's very, very important to recognize when you have a function and when you do not. So here, this one would pass the vertical line test, and this circle, if you notice right here, bam and bam, that intersects it twice, therefore a circle is not a function. It's a mathematical shape that we can kind of modify and look at. If I take it away, half of the circle away, if I only look at this part as a semicircle, that would just be a function, but as a whole, it is not. Now, on the reverse side, when we were talking about the definition of a domain or a function, we were talking about the domain of that function. What are the possible x values that I can put in, and what kind of values am I going to kick out when I have this range of a function? So we're going to talk about the domain and range of any function. So this is a kind of a precursor somewhat. It's kind of nice to have the graphs. I know that we don't have the graphs until next section, but we can talk about that. So if I look at this function, this is a polynomial function, x squared minus 3. So is there any number that I cannot square? No, there's not. No matter how pretty or how nasty that number is, we can square any number and subtract 3. So the domain of any polynomial is going to be all reals. Now that is the way that we do the all real symbol, but if you have interval notation, if you recall, we have from negative infinity to infinity would constitute a domain of all real numbers. So this, if you have not seen interval notation, basically does not include these values that are in here. It means that I start at negative infinity and I go all the way to infinity. So that would give me that in interval notation. When I look at the range of this value, well, if I have any number and I square it, I'm going to get a positive number. When I subtract 3 from that, that's going to give me something that is above negative 3. Now, the lowest that this could ever be would be 0. So if I put 0 in there and I subtract 3, that's the lowest that my parabola in this case would ever be. So we could say that y has to be greater than or equal to negative 3. And so, by interval notation, we would constitute, since I have equal to, it would be from negative 3 all the way to infinity. And I'm going to open parenthesis that at the end. Now, in the next section, it might be a little bit easier to do some domains. If you recall with this parabola, it is transferred down or transformed down 3, and it does something like this. So if you have the graph of it, and you're welcome to use like Desmos online, or graphing calculator to double check a graph at this point to kind of get yourself familiar with it. I'm cool with that. All right, so let's look at this guy. G of x equals the square root of 9 minus x squared. This should be something that you recognize actually as a semicircle, like what we were talking about up here. So this is a semicircle actually of radius 3, where radius is equal to 3. This, by definition, would be the radius squared. But we can also constitute that as looking as a radical function. In real numbers, we cannot have a negative underneath that radical. So if you have a radical, that means that we have to take what's underneath there, which is what's called the radicand, and set that greater than or equal to 0, because it's okay to be 0, and it's okay to be positive, but it is not okay to be negative. Now here's the case where we have an inequality with a quadratic. Again, this is some of that review that you should possibly be coming to me with. Actually, not possibly. You should be coming to me with. And so by factoring this expression, this is a difference of 2 squares. So, some books call a squared minus b squared is equal to a plus b times a minus b. This would be 3 minus x and 3 plus x. So in a quadratic inequality, we will be able to figure out that where are the 2 zeros. This is the way I always taught it. What makes this guy 0? 3 minus what number is 0? That is 3. 3 plus what number is 0? And that would be negative 3. So in a situation like this, this would be our roots or our zeros. And so I want the product of these two guys to be greater than or equal to 0. So here we're going to choose any number in these regions. I'm going to choose like negative 5. If I put negative 5 in here, 3 minus a negative 5 becomes an 8, which is positive. Then 3 plus a negative 5 is negative, so a positive times a negative, because we're multiplying those two things, ends up being a negative. If I throw 0 in there, that becomes 3, that becomes 3, so a positive times a positive is a positive. And if you check any number here on this side, say 10, 3 minus 10 is negative, 3 plus 10 is positive, a negative times a positive is negative. So we want the product of those things to be greater than or equal to 0. Well, are negatives greater than or equal to 0, or are positive numbers greater than or equal to 0? It is this. So I'm going to end up wanting all of these values between negative 3 and 3, including. So the domain here that I have for my semicircle function is going to be from negative 3 to 3. That is the interval notation. I think that is kind of what is preferred, but you could also write it as negative 3 less than or equal to x, which is less than or equal to positive 3. So that would be the inequality. Now, the least that this could be if I have a semicircle of radius 3, again, that's why this part here might be just a little bit tricky without us reviewing some of the graphs. Here's my semicircle of radius 3. Well, here is where my domain lies on the x-axis from negative 3 to 3. But on my range, on the y-axis, we start from 0 and we go all the way up to 3. So the range here is going to be from 0 to 3, including both of those. So that's why I have a bracket versus a parenthesis. And if I want to try the inequality, 0 less than or equal to x, which is less than or equal to 3, would be my answer. Okay? All right, very good. So we're going to move into a rational function. This is a fraction called a rational function. We're looking for the domain and range. So in a rational function for the domain, you want to really, really hone in on the denominator, because there's one thing that we cannot do with a fraction. We can't have a 0 in the bottom. So for our domain, we want to restrict where the denominator is equal to, or where we want to keep where the denominator is not equal to 0. We want to restrict out where it is equal to 0. So that would be what we have in question. So where is x minus 1 not equal to 0? Well, we can just add over 1 and say that x is not equal to 1. That could be my domain. But if I want to write it as interval notation, I want to show you that as well. We would go from negative infinity all the way up to 1. I would skip over the 1, so I got to bring in that union, and go from 1 to infinity. I think I did too many zeros. Yep. Okay. So that would be my domain. Negative 1 to 1, union 1 to infinity. And so what do we know about our range? Well, that's where we have to kind of work with this rational function. If I were to try to factor the top, I would get an x minus 2 and an x minus 1. So if you are not a good factor, you probably need to talk with me and see me or watch some Khan Academy things and do some review, whatever the case may be. But you have to be a good factor. So here I'm going to be able to cancel out the x minus 1s and x minus 1s, leaving me with this x minus 2. So if I say f of x is equal to x minus 2, I hope you recognize that as a y equals mx plus b. That is the equation of a line. So that means I go down 2 on my y-axis, and with a slope of 1, then I would go up 1 over 1 to my next point, up 1 over 1 to my next point. But at 1, at x equaling 1, I don't have a point. So I'm going to open circle that, and I'm going to draw this line around that. So basically I end up having this rational function. It turns into a line where x equaling 1 is not defined. There's a hole there, okay? So that means that there's every y value that's going to constitute except right here when x equals 1. Well, what if I put 1 in there? 1 minus 2, that's at y equaling negative 1. So I have to skip over negative 1. That's the only y value that is not in my range. So my range is going to be y not equal to negative 1, or I could say negative infinity to negative 1, union negative 1 to infinity. And that would give me my range in interval notation. Okay? So again, work with those. This section might be a little bit wonky just because we haven't reviewed all the graphs yet, but it is doable if you have some of that good background with you. So let's talk about this practicality or a real world situation. At time equaling 0, a stone is thrown vertically upward from the ground at a speed of 30 meters per second. Yes. Its height is above the ground. Actually, that should be not 30. That should be 40. Excuse me, I think. All right. So anyway, we're going to work with that function. Neglecting air resistance, f of t is equal to, nope, I think that should be 30. I'm messing myself up here. Okay, never mind. We're just going to work out the function. F of t equals 40t minus 5t squared, where t is measured in seconds. We're going to find the domain and range of f in the context of this particular problem. So that means that I have a stone that is thrown vertically upward from the ground, and it's going to go up and come back down. Now that may be a little extreme, okay, on the arc, but that's kind of the idea of what happens. And that function there is represented by 40t minus 5t squared. So there's going to be two places at which that rock or stone is at the ground level. That's going to help me with my range. Or my domain, excuse me. That's going to be my domain. This part's going to be my range, okay? So how would we figure out where these times are? Well, that would mean I would need to be looking for t. So if I have 40t minus 5t squared, I want to know when that is equal to 0. That's my ground level. So if I want to solve this quadratic equation, hopefully you recall that you must factor a quadratic equation first and then figure out what its factors equal to make it 0. So I'm going to take out any common terms, which is a 5t, and I'm going to be left with an 8 minus t in the end, which we're going to be looking for when does that equal 0. So I go to this factor, and 8 minus what number equals 0? Hopefully you tell me 8. And 5 times what number is equal to 0? Don't make this one out front too hard. This is going to give me 0 as one of my points. So that means over here that at t equals 0 and at t equal 8, that is when we're on the ground, constituting the domain, which means I go from 0 to 8, including both of those t values. Now, the range, like I said, is going to be the y values which go from here to here. So I know I'm going to be starting at 0, but the question would be, how high does this go? Well, if it has kind of neglecting air resistance, we're going to assume that it's a nice parabolic shape. So where does the maximum occur between this 0 and 8? I'm hoping you're telling me that it's halfway in between. So that means at t equaling 4, I need to figure out what the range is. Well, f of t is the height. So I need to plug in 4 into each one of these. So if I do 40 times 4 minus 5 times 4 squared, I'm going to get how tall that this is. So this is going to give me 160, and this is 80 when you do 16 times 5. 160 minus 80 does give me another 80. So the maximum height of that, creating the maximum range of that function, is 80. So range is going to be from 0 to 80. All right, very good. So that's kind of review domain and range. We're also going to add in a different operation of a function called a composition, and I hope that you've seen that before. We also have other operations within a function, as you see here, where we can add, subtract, multiply, and divide them, but we can also end up doing a composition. So it's like a function within a function. So given two functions, we're going to call them f and g. The composition function, now it looks like fog. And do not get this confused with this, which is multiply. Now, sometimes if you see that with a solid dot, that is multiply. The open dot is the composition. It is defined by, some students call that the fog function. F of g of x is defined by doing some evaluations here with two functions. Again, a function within a function. So the domain of our composition consists of all x values in the domain of g such that g of x is in the domain of f. Okay, so basically you just have to have everybody's domain in check. And if you have an overlap of that, you need to make sure that it is restricted to all functions there. So we're going to kind of do this a little bit in a couple different ways, by a graph, as well as a chart, and by our functions before it's all said and done. So we're going to use this following graph to evaluate these functions. So that means the composition, we could write it as f of g of 6, but this way is normally not used. We like to see it normally with this. So that means I'm going to start from the inside and work myself out. I need to first look at g of 6. Now remember, any function at an x value is going to kick out its y value. So I need to look at what is the y value on the g function when x equals 6. So we go to x equaling 6. I find the g function, which is this pink one or red one, and I'm going to go up and I'm going to find what that y value is. Well, come over here. It is 1. So g of 6 is equal to 1. There's the x, y value. That is the point 61. The x value is here. I want to know what y value kicks out on the g function. It is 1. So that reduces me down to this, where now I have to do it again. But now I'm going to be looking on the f function when x equals 1. So I go to x equals 1, go all the way up on the f function. We are at 6. So therefore, f of 1 equals 6. So there's not a lot of work to be done. You just have to kind of know where you're looking. So we're going to start on here, f of 4. We're going to work on the inside going out. So I need to go to x equaling 4 on the f function, which gives me 8. So f of 4 is equal to 8. Now I need to rewrite this outside function. I need to take 8 on the f function. So if I go over to x equaling 8, up here on the f function, looks like f of 8 is equal to 6. Next one, g of f of 6. So that is the reverse of what we have up here. Will it be the same? I don't know. Sometimes it will, sometimes it may not be. So here I'm going to take x equaling 6 on the f function, gives me this guy, which is 5. So now I need to look at what is g of 5. So I go to x equaling 5, kick up on the g function. Notice here I'm right here at y equaling 1. Therefore 1 is the entire answer there. Now, look at this guy. The last one I give you is a composition of 3 functions, actually. That just means we're going to do it 3 times. Don't panic. So, actually, I'm going to make that now a 4 instead of an 8. So make sure you change that. Make that a 4 instead of an 8. So, I want to now take 4 into the f function. So, where is x equaling 4? Up here is my y value of 8. So, I now have f of g of 8. F of 4 gives me the 8. And so, take the 8 onto the g function. So x equaling 8 on the g gives me a 2. And my final work is to figure out what is f of 2. So go to x equaling 2, go up to the f function, and I'm about right there. So I'm going to constitute that as like a 4.5. So if you ever have something like that, guesstimate, and you should be okay.